Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be talking about another constraint that is to be satisfied in our constitutive relation, namely the principle of dissipation. So to come to the discussion of principle of dissipation, we need to introduce some basics. So we start with some basics. So the idea is we will eventually be talking about the principle of dissipation. So we have the entropy inequality. We start with the concept of entropy, and also we talk about the so-called entropy inequality. So to formulate the constitutive relation, we need to understand the role of entropy, so as well as the role of internal energy. So to formulate the constitutive relation, we need to identify the role of internal energy, let's say chi, and the entropy, which is eta. And so let us now write down the energy balance law. So the law is that ddt of integral, the rate of change of the total energy, the time rate of change of total energy is sigma rho half v square plus chi dx is integral alpha of t to beta of t sigma rho v f of dx plus sigma v tau x from alpha to x equal to beta is the total change in energy. So again, this right hand side is being derived from our Reynolds transport theorem and Du Bois-Reymond's lemma. And of course, the second term on the right hand side are the contribution due to surface forces, and the first term is of course due to body forces. Okay, so then we can from this relation we can directly use the Reynolds transport theorem and the Du Bois-Reynolds lemma to arrive at rho d chi dt, where our internal energy is now taken the variable chi, is equal to tau dv partial v partial x. So now so this is directly from the application of these two results on the energy balance law. So let me call this result as 1, and now let us also further define our variable eta. So eta is the entropy density. So this is the entropy density. So by second law of thermodynamics, we have that d eta dt is greater than equal to 0. So the so-called Clausius-Duhem inequality. So it merely says that the entropy of the system always increases with time and hence the inequality. Clausius-Duhem inequality. So let me call this as our inequality number 2. So and let us now also, and this is under the assumption, of no entropy flux. No entropy flux. So then let us also further introduce the concept of free energy. So we have the standard concept of Helmholtz free energy, energy density. So Helmholtz free energy density, we call this psi. So psi is equal to chi minus theta times eta, where theta is the absolute temperature. Theta is the absolute temperature, right? And our psi is the energy remaining to do work. So psi is the free energy density, or it is the energy remaining to do the work. So whatever energy is remaining, or the free energy which is remaining to do the work. So now let me call this as our relation number 3. So free energy is related to the internal energy as follows, and entropy as follows. And from our relation 2 and 3, the Clausius-Duhem inequality and free energy, we get that minus rho times d psi dt plus tau times partial v partial x is greater than equal to 0, or this is the so-called reduced entropy inequality. Reduced entropy inequality. Okay, so this is my reduced entropy inequality. So in the material coordinate, we can rewrite this inequality number 4. So in material coordinate, we can rewrite this as minus r naught partial psi partial t plus t times partial v partial x is greater than or equal to 0. So we call this inequality in inequality number 4a, which is the material coordinate version of the Eulerian reduced entropy inequality. So these two are identical based on the frame. So now I think with all these results, I am ready to discuss the principle of dissipation. So what the principle says is, let me call this as B. The first A was the principle of frame indifference. This is the next principle, the principle of dissipation. So what it says is that a constitutive law must satisfy the reduced entropy inequality, for or for A, whatever the frame of reference is, for all physically consistent values of its argument. Okay, so let us look at this principle via an example. So for elastic material, let us say we have a constitutive relation of the following form. So for elastic material, we have the general form of constitutive law in spatial coordinate as follows. Spatial coordinate is given by tau is tau of ux, or this is equivalent to psi is psi of ux. So either the stress relationship in the form of stress or in the form of free energy. So we have that d psi dt is equal to psi prime d dt of ux, or we have that psi prime 1 minus ux vx. So this is also equal to psi prime 1 minus ux vx. This is again using our tables of material and spatial derivative conversion, tables of conversion. So we are getting this relation from our table of conversion, and let us call this relationship 5. So now from relation 4, which is our reduced entropy inequality, and relation 5. So from 4 and 5 we get the following relation. So tau minus rho times 1 minus ux times psi prime ux vx is greater than equal to 0. And then from so from principle of energy dissipation, we can say that the inequality, this inequality star holds for all Vx. So from the principle of energy dissipation B, we see that the inequality holds for all x, for all Vx, and we get that this is tau is rho 1 minus ux times psi prime ux. So tau holds for all ux, and this is the case. And similarly in the material coordinate, we find that the relationship is T is R naught psi prime of ux. Psi prime at ux. We call this first relation as relation number 6, and in the material coordinate the corresponding relationship is 6a. Okay, so then so what we get now is that when the material satisfies the principle of dissipation, then the stress strain relationship depends on the free energy of the system, and such a material are also known as hyperelastic material. So what I just said is the following. So for elastic materials for which stress is a function of free energy, this is the set of materials also known as hyperelastic material. And also we can also say that free energy in this case, free energy is a function of strain. The free energy is a function of strain. Let us look at this idea through one quick example. So for a linearly elastic material, we have that T is E times ux, and from 6a, the material coordinate equation, we see that R0 times psi prime epsilon is equal to E epsilon, right? So we have chosen a linearly elastic material. So R0 psi prime epsilon is E epsilon, or we have R0 psi of epsilon is, we integrate this equation, E epsilon square by 2. This is by taking the constant of integration to be 0. Constant of integration to be 0, and that is what we have. So now we can, so this is what we have in the form of free energy, when the free energy depends, when the stress depends on the free energy. Okay, so then if we choose our stress to be the stress related to that of the spider silk material, so A times B epsilon minus 1, where B is non-zero, we again get that from our material coordinate equation. R naught psi prime is equal to A e to the power B epsilon minus 1. And then we see that R naught psi, when integrated, is going to give us A by 1 by B times e to the power B epsilon minus epsilon. Okay. So then let us look at one more example. So for a viscous fluid, we have tau is tau of rho comma Vx. So now we assume that, suppose psi, here tau is for a viscous fluid, which means that there is no elasticity in the material. We assume that the stresses depend on rho and Vx. So these are all frame indifferent variables. So I think we have noted. So frame indifferent variables are this and this. Okay, so tau is a function of rho and Vx, and then we can assume that psi depends on the same quantity. Psi depends on the same quantities, that is rho and Vx, and we can use the Clausius-Duhem inequality, the Clausius-Duhem inequality, to get that the relationship behaves as Vx tau plus rho square partial psi partial rho minus rho times partial psi partial Vx times d Vx dt. This is greater than equal to 0. So just placing all these details, we get that this is, so we call this relationship as star, and then if we use our continuity equation, we see that we have rho t is minus v times rho x minus rho times Vx, and since we have that star must hold, we get the following relation. So what are we saying is, so since star must hold for tau equal to minus rho square partial rho psi, we have that rho times partial psi partial Vx times dVx dt is less than equal to 0. Okay. So we get to this form of the inequality from the Clausius-Duhem case. So now notice that this material derivative capital dVx dt must either be less than 0, or it can change sign. It can either be less than 0 or greater than 0, depending on whatever the value of Vx is, which means that we must have that partial psi partial Vx must be equal to 0. Okay, so what we have is that since we have that dvx star dt is less than equal to 0 or greater than equal to 0, then we have that partial psi partial vx is equal to 0. We have the following, although tau may not depend on vx, although tau may not depend on Vx. Tau may not depend on Vx. It turns out that free energy does. Free energy does. Okay. So tau may, well, although tau may depend on Vx, tau is the stress, it turns out that free energy does not. Free energy does not because the rate of change of free energy with respect to Vx is 0. So the free energy does not. Okay. So then let me call this relation as double star. And now let us look at for a very specific class of viscous material, or the so-called linear viscous material. So for a linear viscous model, we have that tau plus rho square psi rho is alpha plus beta times Vx. So we call this as our triple star relation. So tau plus rho square times psi rho is alpha plus beta Vx. So then using all these relations, so using star, double star and triple star, we find that alpha plus beta Vx times Vx is greater than equal to 0. And this relation must hold for all Vx, right? That is, even when alpha equal to 0 and beta greater than equal to 0, it must hold for all Vx. So what we get is that since now I am going to introduce a new variable P, which is the pressure. So let my pressure P is rho square psi rho. Psi rho implies partial psi partial rho. So from here I see that tau, from here and relation number 3 star, I see that tau is equal to minus P plus beta times partial V partial X. So I get my relation, the stress strain relation in the form of an extra variable, which is the pressure. So now it turns out that the constitutive relation between tau and the strain rate has introduced a new variable pressure, for which we also need to know the equation of the state. So this is my constitutive relation, which has an additional variable, a constitutive relation which has an additional variable in the form of a pressure P. So we need an equation of state. So for this we need an equation of state. So what should given an equation of state, we should be able to completely describe the material with the constitutive relation. So then the question that we are trying to ask is how to completely solve the model for elastic and or a viscoelastic material. So let us recap. So for elastic or viscoelastic elastic material, we have that for example, for linearly elastic material, for elastic material, we have the constitutive law given by T is equal to E times Ux, and this is the so-called Young's modulus. And so if this is the case for linear elastic material, if we plug it into our momentum equation in the material coordinate, so for linear elastic material, if we plug our relation for the momentum equation in the material coordinate, we see that we get UTT is equal to C square Uxx plus F, where where my C square is Young's modulus E by R naught, which is the initial density. Okay, and this whole equation now is a non-homogeneous wave equation. We have seen it a few minutes back in one of our module, that this is the non-homogeneous wave equation. Okay, and basically this momentum equation or the non-homogeneous wave equation can then be solved either directly or analytically using the method of D'Alembert, the D'Alembert's principle, or we could also use the method of Laplace transform to solve the same. I think I am all out of time in this module, and in the next module I will quickly show you how to solve this momentum equation or this non-homogeneous wave equation, first using the method of characteristic or the D'Alembert principle, and then I will introduce the Laplace transform and show the solution methodology with the Laplace transform. So thank you so far for listening.